Hey everybody, and welcome to another tutorial. I'm Brad. I'm the creator of Expanse, the volumetric skies, clouds, and atmospheres plugin for Unity's high definition render pipeline. And today we're going to be talking about how to optimize Expanse for your game. Say you have some kind of strict frame time requirement or a strict FPS requirement. Expanse might be too expensive, at least at its default settings, for you to hit that requirement. And today we're going to talk about what things that you can tweak and what parameters you can change to make Expanse render faster, more efficiently, and to help get Expanse into your frame budget. So before we jump over to Unity and start looking at stuff, I just want to make a distinction between two types of performance optimizations. One sort of performance optimization is a purely algorithmic performance optimization that has nothing to do with visual fidelity or quality. It's just basically making something faster without really changing the result that it gives you. And these sorts of optimizations are things that I can do on the code side of things, and I'll check them in every once in a while, and when I discover them or come up with them, I'll put them in updates, and you sort of won't even have to think about them or know about them. Expanse will just get faster. The second kind of optimization is the kind that we're going to talk about today, and those are optimizations that essentially trade visual fidelity for better performance. So you have the clouds, they render and they look great, right? But maybe it's too expensive, so you do some things to degrade their quality, and it makes it faster, but they look a little bit worse. And the question, as a 3D artist, especially a 3D artist working in real-time graphics, is how do we set those parameters and make those trade-offs such that the impact on visual fidelity is minimal, at least it's not that noticeable for our specific application, but we gain a lot of performance back. So that's what we're going to be looking at. In this video, I'm going to give you a strategy that's not foolproof, but I think will work for most cases for how to set Expanse's parameters to optimize for your use case. And hopefully you'll give it a try and you'll get some performance back in your game. Something I should mention, by the way, before we get started is that I am using a 2080 Ti on Windows 10 using D3D11 as my graphics API. You might get varying results with DX12 versus DX11 or Vulkan if you use Vulkan. So there's that, and then the other thing is that a 2080 Ti it's a beefy graphics card, right? So you can expect if you're using a 2060 or 2070 to see performance that's worse, and if you're using one of the 30 series cards, you might see performance that's a lot better. I don't know. All right, so here we are. We're in Unity. I've got a basic scene loaded up with the Expanse Creative Sky prefab in, and I have a couple of pieces of geometry. Just this model of Lower Manhattan that I like to use that I got for free on TurboSquid, and this free mountain that I downloaded from the Unity Asset Store. Let's just dive right into it and see what the different quality settings that we can tweak are. One quick thing actually before we start, I am going to assume that you have some familiarity with Expanse's interface and how Expanse works. If you don't, then just watch the video that I'm going to link somewhere around here, and it'll get you up to speed. So the first thing I'm going to do is I'm going to uncheck the volumetric clouds here real quickly, because that's going to be sort of the second half of the tutorial, is figuring out how to optimize clouds, because that's actually much more complicated than optimizing everything else. All the quality settings that are not related to clouds, you're going to find in the quality settings block. And for the creative sky, that is under other components and quality settings. For the other sky prefabs, there's a quality settings game object somewhere in here that has the quality settings block on it. And if we take a look at this in the inspector, you'll notice we have a couple different categories. One is general, which just has anti-aliasing and dithering parameters. Then there's the clouds category, which we'll discuss in a little bit. And then there's the two categories we're going to talk about now, which are atmosphere and fog. So looking at the atmosphere drop down, we have a couple of different parameters. The first one is the atmosphere texture quality, and this controls the resolution of the textures that Expanse renders the atmosphere into. So Expanse doesn't actually render the atmosphere per pixel full screen. it renders the atmosphere into a series of textures that are optimized for visual fidelity in different areas of the sky. Because the sky is very smooth, you can make some tweaks to how the textures are mapped to make it more efficient to render. And so because of this, these textures aren't just like things that we're going to look up, they're things that we're rendering into. And so the texture quality is going to have a big impact on performance. So this isn't just like we're using 4K textures on our model versus 2K or 1K textures. This is like, we're generating the atmosphere and it's going to be this resolution. And so the algorithm is going to be more expensive to run if we use a higher texture quality. Fortunately, there's not a huge difference between the low texture quality setting and the high texture quality setting. So if we go and we select potato mode and then we select the highest quality, ripping through the metaverse, they look pretty similar. I think the place that you'll notice it most is at sunset. So if you move the sky down here if you change the time of day and then come back to the quality settings and adjust, you can see at sort of the edge here, there's a slight difference in the multiple scattering behavior. You get a little bit more pink color with the low setting. But really, it's like you're really splitting hairs. I would recommend using the highest setting that you can tolerate just because you're less likely to have visual artifacts. But if you have to set it to a super low quality, for the atmosphere, it's not a huge deal. It'll still look pretty good. Cool, so with the sun back up in the sky now, we can look at some of the rest of these parameters. And the next ones to look at are these sample count sliders. The way that Expanse renders its atmosphere is it ray marches a volume of simulated like atmosphere particles, atmosphere density. And the way ray marching works is that it takes a number of samples in that volume of atmosphere and uses those samples to render the color estimate. Because of this, the higher number of samples that you take, the better the visual fidelity of your result is going to be. But you're taking more samples, so it takes the computer longer to do that. So it's going to take longer, right? So it's going to be less efficient. So these sample counts let you optimize every single part of Expanse's sampling strategy. And right now they're set to pretty conservative low values. And you can actually, if you want to, set them even lower and still get a decent result. So I'm actually going to pull the sun back over the horizon again because it's easier to see at sunset. But yeah, if you set now, for instance, something like the transmit its samples to 4, it's still workable. It doesn't look that different. If you set it to 1, it looks wrong. But as you bring it up, it pretty quickly converges on the correct result. Similar for the single scattering samples. Again, if you drag it all the way down, it's wrong. But as soon as you start to get up to like 7, 8 samples, that's enough. 32 is a safe number. And then, of course, you can pull it really high if you want to, but at some point, it's just diminishing returns, and it doesn't even matter. Of course, all of these sampling parameters, are going to depend on the atmosphere that you've built. If your atmosphere is some alien atmosphere that's way denser or way bigger or stretches out further, you might need more samples to cover it. But you can play around with these and sort of see, how low you can take them and still like the result. I think the default parameters are perfectly fine. And they don't have too much of a performance impact. But if you're really trying to squeeze, you can bring the sample counts down. The next thing to draw your attention to is these two checkboxes here that say important sample atmosphere and important sample aerial perspective. Basically what importance sampling is it is a sampling strategy that tries to put samples in the best place possible so that you can take fewer samples and still get a good result. You can really see the effect of this if we bring the transmit its samples down to something like 2 and we have importance sampling on. It's not too different from 12 samples. And if we don't have importance sampling on, it's more different. Again, it's pretty tough. Like they both look decent, right? But importance sampling will give you a better result for fewer samples, at least with the atmosphere textures. With the aerial perspective texture, the important sampling strategy, frankly, it's not that good. I want to improve it, so I would just leave this unchecked for now. If you, for some reason, sort out that it works for you, then use it, but it doesn't really work that well for me, so I just leave it unchecked. And then the last parameter here is this aerial perspective depth skew parameter. And basically, the way that Expanse computes aerial perspective, or the portion of the sky that gets composited over geometry, is it renders the aerial perspective into a lower resolution texture at various depth slices in the scene. And this depth skew parameter lets you position where those depth slices are. So if it's higher up, then the depth slices are closer to the camera, and if it's lower, then the depth slices are further away from the camera. I think it's always good to have this parameter set somewhere above 1, because I think it's more important to capture aerial perspective closer to the camera, where the detail is going to matter more, than it is far away, where it starts to look more and more the same. But you could play around with it, see what you like. It's not really going to affect performance either way. Cool, so now that we've run over what each of the parameters means, I actually want to show you what performance impact they have. And the way I'm going to do that is I'm going to use a tool called RenderDoc. RenderDoc is a visual debugger that you can plug into Unity that will show you all the draw calls that the graphics API makes, or that we make to the graphics API. It's a really cool tool. It's super easy to integrate with Unity on Windows. There's like a default integration where if you have it installed, Unity will just pick it up. And we're going to use it to take some performance measurements. So I'm going to set the atmosphere texture quality all the way up, and I am going to bring up all these sample counts to 128. Great. And now I'm going to enter game mode and hit play. Okay, we're in play mode, and you can already tell that my frame time is 9 milliseconds, which is pretty high, pretty long for just rendering the atmosphere. And if I click the render.capture capture button and we open up the capture and I search for Expanse and make sure that I find the right one, here you can see all of the Expanse draw calls, and you can see these ones right here, from pre-compute transmittance to render aerial perspective, are all of the atmosphere rendering draw calls. And if I hit the time button here, it'll show me how long it takes. And you can see that pre-compute multiple scattering is taking about 4 milliseconds, render atmosphere is taking about 1.2, and render aerial perspective is taking about 1.3. So they're taking a long time. And this is because our quality settings are just so high, and we're taking lots of samples. Okay, so moving back over here, now if I go and I adjust the quality settings and I set the atmosphere texture quality to something like medium, and the sample counts to something like 12 and 12 and 32 and 16 and 12, so the default settings, you can see already that now my frame time is down to about 4 milliseconds, so we've cut the frame time in half. And if I take a capture and I hit the time button again, you can see now that these are taking almost no time at all. So multiple scattering is taking 50 microseconds to compute, and render atmosphere and render aerial perspective are each taking about 100 microseconds, so 0.1 milliseconds to compute. So now you can see we're on the order of microseconds now, for fractions of a millisecond, and now we can see if we can make it even faster. So if I go and I set the quality to potato, and I put the transmittance samples at 4, and the aerial perspective samples at 4, single scattering at 8, multiple scattering at 8, and accumulation at 4, you can see the sky still looks pretty okay. Not that much changed when I changed those sample counts and when I switched the texture quality. And we're going to take another capture. And now you can see the entire sky is rendering in less than 100 microseconds. We've got those two calls that were taking 100 before are now each taking 30. The multiple scattering call is taking 12. It's really going fast now. And I mean, we can move the time of day around, and it really doesn't look any worse. Not that much, at least. So yeah, that's the way that you can optimize rendering Expanse's atmosphere. I think we've optimized it like very aggressively, and you could easily budget more of your frame time for rendering the sky. But if you have to, you can really make Expanse's atmosphere render extremely quickly. Okay, so making our way down to the next drop down here, it's the fog drop down. You can see we have 4 parameters here, but none of these 4 parameters is actually going to affect performance the most. There's another parameter that's on a different block that will affect performance more than any of these 4 parameters here. And that parameter is on the fog, on the atmosphere layer block for the fog. Geometry and cloud shadows, these 2 checkboxes. And what these do is they specify if the fog should have volumetric shadows. So if I uncheck it, there's no shadowing that happens. And if I check it, then we get these cool streaky God rays. And volumetric shadows are the expensive part of Expanse's fog. Without the shadows enabled, if we take a capture, render screen space volumetrics takes about 60 microseconds, which is, almost no time at all. And now if I check if I check geometry shadows, and I take another capture, you can see our 60 microsecond draw call has been replaced by 150 microsecond draw call and another 4 millisecond draw call, which is crazy. That is a lot of time. We have not optimized these volumetric shadows at all. I have them set to a pretty high quality preset right now. But this is just proof that volumetric shadows are the thing that we're going to be trying to optimize here about the fog. So making our way back over to the quality settings block here, you can see the first parameter here is going to have a big effect on the volumetric shadows and how they look, and also how long it takes to compute them. And that is the screen space fog quality. And this controls the resolution of the texture that Expanse renders its fog into. Because it's the same thing, the same logic as for the sky texture, it's not just a texture we sample from, it's a texture we render into. So it's going to have a huge impact on the performance. Its resolution is going to grow the complexity of the algorithm. So if we set this to potato and we take a capture, you can see that 4 millisecond call has now been reduced to 1.7 milliseconds. So this improved performance by a little more than 2x. So it's still 1.7 milliseconds is a long time. I think we can do better than that. So let's take a look at some of these other parameters. And by the way, when you adjust this, it's going to have an effect on the way the shadows look. So potato quality, they're kind of soft. You can start to see some little artifacts at the edges. If I go all the way up to the highest quality, then they're very sharp and clean. So the next parameter to talk about here is the next one in the list. This is screen space occlusion samples. And this basically is a control for how many samples we're going to take to estimate the volumetric shadowing. So if we turn this all the way to 1, which is just take 1 sample, it looks horrible and unusable because we're only taking 1 random sample for every pixel, every frame. And so we're getting a terrible estimate of the volumetric shadowing. And as we turn it up, we start to get better convergence until eventually we have no more artifacts. So I'm going to set this to something like 40. I think that looks pretty good. This next parameter, the screen space fog depth skew, it's the same idea as the aerial perspective depth skew. It gives you control over the priority of the depth aligned slices. I'm not going to talk about it too much because it's not too important. The screen space depth downscale, however, is an important parameter for performance. Basically what this does is it says when you are sampling from the depth buffer to estimate these screen space shadows, you can downsample the depth buffer first and get better cache coherency when you sample it, so it's cheaper to take samples. So if we set this down to something like 3, you can see we have minimal visual impact, but it's going to make things more performant. So I'm going to take another capture, and this is with the reduced sample count and the smaller scaled down depth buffer. And you can see that now instead of taking around 1.7 milliseconds, we're down to 200 microseconds. So it's way faster. So we've been able to improve the performance of the volumetric lighting from in the volumetric shadows from around 4 milliseconds to around 200 microseconds. And 4 milliseconds sounds like basically untenable, totally impossible to include in a game with a frame budget that of around 16 milliseconds, so 60 FPS. But 200 microseconds, that sounds doable. Something else to note is that the cost of the volumetric fog is actually going to depend on what type of volumetric shadows it's casting or it's receiving. So if you pop over to the celestial body object for your sun, you can see that there's a checkbox here for shadow map volumetric shadows. And if you check it, you'll notice the shadows change a little bit. And the reason for this is that when this checkbox is unchecked, volumetric shadows are computed, as I've kind of alluded to over the past minute or so, in screen space using the depth buffer. So they're less accurate, but they still work, and they require no shadow map to function. However, if you check this, it uses HDRP's shadow map for the directional light, and the resulting shadows are more accurate, but they're also going to be a little bit more expensive if instead of sampling against a downsampled depth buffer like we were doing before. So just to give you a sense of how much more expensive, I'll take a capture with this on. And you can see that this is now around 260 microseconds, where before it was around, like 180 or something. So we've lost about 80 microseconds of performance sampling the shadow map and using the shadow map instead of computing these shadows in screen space. It's not too bad, but just something to be aware of. So, you might be saying, wow, Brad, 260 microseconds, that's a decent amount of time for a 16 millisecond frame budget. I don't know if I can afford to use that. And to which I would tell you, okay, well, let's take a look at, I understand your frustration, and, it's definitely a non-trivial amount of time when you're sort of planning out your frame. But I would tell you, okay, well, let's look at how long Unity's volumetric fog takes to render. So if we go and we disable Expanse's fog, and we grab a global volume and enable Unity's fog, which looks completely different, and I have a hard time getting it to look the same. So I think there's just some kind of algorithmic difference between how they handle things like anisotropy. Okay, so now if we take a capture and we search for volumetric, we see Unity's two draw calls, volume voxelization and volumetric lighting, and we'll see that theirs takes around 300 microseconds in total. And so it's similar to Expanses when you fully optimize Expanses. And the other thing is that you'll notice that this is the low quality volumetric lighting. If you check in the HD render pipeline settings, volumetric's high quality, which is, I think, on par about with Expanse's medium quality volumetrics, just in terms of texture resolution. That's sitting at about 500 microseconds and then 1500 microseconds. So that's about 2 milliseconds to compute the high quality Unity volumetric lighting. So the moral of the story here is that volumetric fog is pretty expensive, and volumetric shadows are expensive to compute. And 2 milliseconds is for high quality volumetric fog. It's about par for the course. It certainly is at least par for Unity's implementation. And 200 microseconds for volumetric fog that's not as high quality is about the same as what Unity offers performance wise as well. Whew. Okay, I got to take a break for a minute before I start talking about the cloud stuff, because that's going to be even more intense. This is just the preamble. The cloud stuff is more complicated, but we'll make it through. Maybe I'll put a break here in the video. Everybody can just go get like a glass of orange juice or something, rejuvenate, recharge, take a break. Okay, I just went to go and get a glass of orange juice actually, and I found that my orange juice bottle has just blown up. and it's got a bunch of gas in it, and I think that means that this has fermented in my fridge. And it's only, this is May 22nd. I'm filming this on May 23rd. It's just May 22nd. So it's 1 day past the expiration date, and it's already fermenting. So I guess moral of the story is drink your orange juice before it expires, because now I don't want to drink this. I feel like this is gonna, it's like too early for a little orange cocktail. Okay, so let's take a look at how we can optimize rendering clouds with Expanse. The first thing I'm going to do is re-enable those volumetric clouds I disabled at the beginning of the tutorial. You can see we've got them here right now. And I've got the settings pretty high right now. So let's just take an initial capture just to see how we're doing performance-wise. So if I just search for cloud in RenderDoc, it should come up. So you can see here that the total time to render the sky is about 14 milliseconds. and you can see here, render cloud layer 0 down here is taking up 12 of those milliseconds. And you can also see render cloud shadow map 0 is taking about a millisecond on its own. And then there's some additional draw calls to blur and composite. But you can see that it's taking a long time to render these clouds right now. So we have some serious work to do to optimize these things. And just a reminder, I have it set at a very high quality preset right now. So when you open up the default cloud preset, you're not going to see it taking 13 milliseconds to render probably. But this is more just for instructive purposes to show you just how expensive it can get. So when we talk about optimizing cloud rendering with Expanse, there's sort of two things that we can do to make our clouds render in a way that's more performant. The first category of things has to do with how we sample the cloud density distribution, and that means how many samples do we take? Do we have any optimizations around like which samples we consider are important and which ones are not important? Which samples do we light and which samples do we avoid lighting? So there's sort of that category of sampling strategies. And then there's another category, which I'm going to call kind of like frame reuse or data reuse. And this basically says, can I do less work every frame and reuse data from previous frames to supplement the work that I'm doing in this frame? This is kind of the same principle that techniques like temporal anti-aliasing and temporal denoising use. And Expanse also sort of leverages that principle to be able to do less work every frame and to improve performance. But of course, this also can come with its own visual trade-off of possibly little artifacts that you see, or blurring if the camera moves very, very quickly, or if that occlusion changes very, very rapidly. So these are all things to consider. But those are the two categories we're going to look at: sampling and temporal reuse. Okay, so with that said, I have a 4 or 5 step process. Maybe it's more step. It's a multi-step process. Some number of steps that I'm going to share with you. That is the way that I like to optimize clouds for rendering with Expanse, and the way that I like to sort of do the visual fidelity trade-off. It's not necessarily the right way. There are other things that you can do, other strategies you could use, I'm sure, that would give you great results. But I will say there's definitely a wrong way to optimize clouds for Expanse, where you'll end up trading way too much visual fidelity for very minimal performance gain. And this strategy, if you follow it, will have you avoid falling into that trap. So the first thing that we're going to do is we are going to go to the procedural cloud volume block. So the first thing that we're going to do is actually going to have nothing to do with this quality foldout in the procedural cloud volume block. It's actually going to be in the noise editor foldout, and it's going to be this setting, noise texture quality. And we are going to set this to high to start with. We're going to keep it at some setting that is pretty expensive and maybe more expensive than what we're ultimately going to want to end up with, but it's going to give us a good visual baseline to start with, something that looks very good, right? And we're going to lower this later, but we're first going to try and use other strategies to optimize these clouds, and then if need be, we'll lower this texture resolution later. So moving over to the quality foldout, the first thing that we're going to do here is we're just going to take this reprojection frame slider and we are going to crank it as far to the right as we can tolerate. And you can sort of notice if I go back to the scene view here, if I slide reprojection frames all the way over to the right, I really don't see that much of a difference. It looks pretty good. There's a little bit of blurriness, but not too much. And what reprojection frames does is it basically renders just a portion of the clouds every frame, and then uses previous frames to grab the other results. And it takes into account the motion vectors of objects and the motion vectors of the camera to make sure that it takes those previous samples and puts them in the right spot. So the more reprojection frames that we use, the less work we're doing every frame, and the more work we're reusing. So I think that looks, I'm just going to set it to 4 because I think that looks pretty decent. One thing to note is that if you're using temporal anti-aliasing, if I turn that on, then this can really blur the clouds quite a bit when you're using reprojection. So you might have to use something more like 2 reprojection frames or 3 instead of all the way at 4 if you want to get a result that's not extremely blurry. But, you know, that's also sometimes just an artifact of scene view. Sometimes in game view with TAA, it can look better. So yeah, I'm going to use 4 reprojection frames. And I'm going to go to game view again. And I'm going to hit play. And I'm going to take another capture. And you can see already that this has brought down our render time from 13 milliseconds to 2 milliseconds, 1.8 in particular. And our shadow map is still taking 1 millisecond to render because we haven't done anything to optimize that. But it's taking, yeah, this is now taking 2 milliseconds. So we've significantly increased the performance already with a minimal visual trade-off, depending on whether or not we're using temporal anti-aliasing, so that's the first thing I would do is you just set that reprojection frames value to something as high as you can tolerate. Great. Okay, so now we can do some more stuff. So that the next thing I would suggest doing is if this is still not performant enough for you, say you were only able to go 2 on the reprojection frames, right? And it's not performant enough for you. You can start to play around with these sample counts, this coarse step range and detail step range parameters. And these are basically the sample counts on the left-hand side here, the lower end of the range, the number of samples that it uses for close-up clouds, and the number on the right-hand side of the range, the number of samples it uses for far-away clouds where it has to sample way more clouds. Because close-up, you're just looking through a small portion of the cloud volume. Far away, you're looking through lots of different clouds, so you need more samples. I have these set pretty high right now, and I get the feeling that I could lower them quite a bit and without having visual artifacts. And just to note, like I'll just show you what it looks like if I lower them too much. So if I lower them a lot, you can start to see that I get these little like flickering, this like flickering happening, and this kind of noisy thing happening around the edges of the clouds. So that, you know, that's undesirable, and so you're going to want to make sure that that you select a sample count that mitigates that, so you don't see it. So I'm going to set my coarse step range to, on the right hand side, 32, and on the left hand side, 16. And my detail step range, my maximum I think is going to be 64, and my minimum is going to be 32. I think I have to bring it up even just a little bit more, something like 48 and maybe 78. Yeah, that looks pretty good to me. So now I'll set my reprojection frames back to 4 where I had it before. And now with those updated, better sample counts, I'll take another capture and see how long it's taking. Great, and now you can see render cloud layer 0 is now 1 millisecond instead of 2 milliseconds. So cutting the sample counts, about in half has cut the time about in half. So it's going even faster now. We're at 1 millisecond. So if 1 millisecond still is not fast enough for you, then there's other things that you can do. And so that the next thing that I would recommend you do is you come down to the media 0 threshold and the transmittance 0 threshold here. And by default, they're set to 0.0001. This is a very small number, and you can probably get away with a higher number, like 0.01, and it'll still look fine for both of them. And just to explain what these both do, these have to do with termination conditions for the ray marching loop. So higher numbers mean it'll terminate more frequently, and the price you pay is that you might miss some portions of the cloud that aren't very dense. But the win that you get is that you terminate the ray marching loop earlier, and it's more performant. So taking another capture with those at 0.01. And you can see that's shaved off about like a couple, maybe like 50 microseconds or something. So we're now starting to get numbers down in the 900s instead of all in sort of the upper 1000s for microseconds. So not a great, huge optimization, but enough where it might make a little bit of a difference for you. Okay, the next thing that you can do to further try and buy some performance is you can decrease these step ranges until you have noticeable visual artifacts. So I'm going to do 8 and 16 and 16 and 32. And now you can see that I've got noticeable artifacts right here around the edges of the clouds. Because the sample counts are so low. And to mitigate these, you can check down at the bottom here, use temporal denoising. And this will use more history frames to actually try to accumulate samples over time and denoise the image and get rid of those artifacts. And you can set the denoising history frames up to something like 16. And that should help to reduce the artifacts you're going to have. In scene view, chances are you're still going to get a number of artifacts, but when you move to game view, it should look a little bit better. And now you're starting to get to the point where the quality trade-off is going to be pretty steep. But if we do a performance capture, we can see that now we're at 500 microseconds for rendering the clouds instead of a millisecond. So we've brought it down to 500 microseconds. And by the way, as a result, our shadow map now renders faster too, because the shadow map parameters for sampling are based off of the regular parameters for sampling. And there are other ways to optimize the shadow map, but we'll dig into that in a little bit. Okay, so say that this is still just too slow for you, and you just need it to go faster. Something that you can do to further optimize it is you can go back to the noise editor and the noise texture quality, and you can set this to a lower texture quality. So I'm using the creative UI, the creative sky. So I actually have to do this in the creative cloud volume here. So I'm going to set the texture quality to low. Actually, let's go all the way down to potato. And you can see that this is now, we're getting to the point where these just don't look that fantastic, but because we're really just pushing the boundary of how fast we can get them to render. But let's take another capture and see how fast they are now. Great, so now we're sitting at about 300 microseconds to render this cloud layer. And just as a reminder, we started out at 13 milliseconds, and we're now at 300 microseconds. That's almost what? That's like a 50x speed up, I think. Maybe I'm doing my math wrong. I don't know. And we're really pushing the limit of how much we can do here, right? Okay, say that still this is not performant enough for you. Maybe you're trying to run this on a machine that has a very old GPU, and you're not seeing 300 microseconds. You're still seeing like 2 milliseconds or something. Something else that you can do is you can pop over into the quality settings block here. You can go to clouds, and this cloud sub-resolution parameter, you can tweak this to be something like 0.5. Now, just for the record, I do not recommend using this parameter. I think that you should just try and avoid it at all costs. That's why it's the last thing that I'm suggesting. Well, it's going to be the second to last thing that I suggest to do to optimize, because this is just going to make your clouds look worse. It's going to, it's like the worst possible strategy for optimizing clouds, because it just says, okay, we're not going to try and do any reuse. We're not going to try and do anything smart. We're just going to render the clouds at a lower resolution and just call it a day. But if you really, really have to, then it's something that you can try and see if it makes a difference for you, if it's a trade-off you're willing to make. So once again, hitting play and just showing you what this looks like by maximizing it. You know, I mean, it doesn't look great, but, you know, it also doesn't look as bad as you might imagine it would. You know, I mean, they're just extremely blurry. And let's take a capture to see how fast this is now. So now this is taking 200 microseconds instead of 300. So we shaved another 100 microseconds off by rendering the clouds at half resolution. And by the way, I do want to make one comment about the sub-resolution parameter. And that is that if you are rendering in 4K, I take back my comment about not using this. I think that if you're rendering in 4K and you don't want to render the clouds in 4K, you want to render the clouds in 1080, but still get the benefit of your geometry being rendered in 4K, then I think this is actually a very good parameter to use. You can set this to 0.5, and it will render everything in regular 1080 instead of rendering it in 4K. Render the clouds in 1080. And just to show you what that looks like, if I set this to 4K, now you'll see that they don't look quite as bad. They're just rendering in HD. And this can really, really help you for 4K, because rendering the clouds at full res in 4K can really get expensive. So say that you're at like the end of your rope and you're like, this is still not fast enough, Brad. We gotta optimize it more. I would tell you, look, there's one more thing you can do, and I don't recommend you do it at all because I just think it looks bad and it's just not great. But you can pop over into the procedural cloud volume here, and you can go to lighting, and where it says self-shadowing, you can just uncheck that box. And now you'll see that the clouds no longer cast shadows onto themselves, and they look worse for sure, I think, but they are going to render faster. And this is the very, very last resort for squeezing performance out of your clouds, is to just disable self-shadowing entirely, because self-shadowing is a big part of what makes rendering these clouds expensive. And some things you can do to fake self-shadowing, you can turn up the vertical probability strength to sort of try to get a little bit of something that looks kind of like shadowing in there. You can bring down the depth probability bias to introduce a little bit of shadowing. And then you could also maybe increase the ambient light to help to bring a little bit back in. And now taking a capture with this, by the way, let's just to show you how bad this ends up looking. If you bring down here, it's definitely not as nice as having self-shadowing on. You could maybe get away with it, but yeah. Taking the capture. Okay, it's now taking around 120 microseconds to render, which is pretty extreme. And I don't even think I've ever. This is my first time trying to pushed it to the very, very limit of how much you could optimize. I don't think I've ever gotten to render these in less than 200 microseconds, but here we are. We're rendering these clouds. They don't look that great. They look pretty bad, but you can render them in 120 microseconds on a 2080 Ti. And they definitely look pretty bad, but maybe in some world this is tolerable. Okay, and I lied. There's actually one other thing that we can do to try and optimize these even more. Say that you are only going to have your game running during the daytime, and you want there to be a moon somewhere in the sky during the daytime, but you don't care if it illuminates the clouds. You can come over to the moon celestial body block, and you can click light clouds here. You can uncheck this, and now only the sun will light the clouds, and the moon won't be lighting the clouds. Of course, this means that when you bring the time of day down, and wherever the moon is, I might need to change what day it is. The moon is no longer going to light these clouds at all. They're just going to receive light from the skybox, but not the moon. But you'll see now that if we bring the sun back up and we take a capture, we're now rendering the clouds in 90 microseconds. So we've gotten down to 90 microseconds. That's crazy. That's like, you should hopefully, if you want to use volumetric clouds at this point, if you were trying to make it this fast, you're just better off using a skybox. But there you go, 90 microseconds for technically rendering volumetric clouds. The last thing we can do here now is we can try to optimize rendering the cloud shadow map a little bit. You can see that we have shadows being cast by the clouds now. It was still taking around 100 microseconds. The way that we can adjust that is we can just go to the clouds section in the quality settings block, and we can reduce the shadow map quality to, I think let's just keep it at low. And now we can take another capture. And you can see now the shadow map is taking about 30 microseconds to render. Okay, so that was quite the crazy exercise. But the point is that if you sort of go in this order, all the way down to eventually disabling self-shadowing for the clouds, turning off the moon, there's a wide range of performance trade-offs you can make. And hopefully this order will encourage you to use things like reprojection and temporal denoising and reducing sample counts prior to just lowering the cloud resolution using that sub-resolution parameter, or disabling volumetric shadow, or disabling self-shadowing, or turning off the moon. That the first thing you'll do is you'll reach for reprojection frames or for the sample counts and temporal denoising, so that you can get a result that looks better and still buy back quite a bit of performance. And things like the texture quality you can try and change too eventually, but before you do that, there are some optimization strategies that will just make your clouds look better, and allow you to sacrifice less. Okay, so I've undone pretty much all those last couple changes that I made to really reduce to really improve performance. And I just want to bring up that if you're using temporal anti-aliasing and you really just don't like the way that reprojection blurs the clouds when temporal anti-aliasing is enabled, it is still possible to optimize things without using reprojection frames really at all. So if we set this to 1, and we reduce our sample counts to something like 8 and 16 and 12 and 24. And then we up the number of denoising history frames to 32 with temporal denoising enabled. And then we hit play and we take a capture. You can see that this puts us at about 4 milliseconds for rendering the clouds. And this is still quite expensive. I think that the reprojection really helps to cut down on the size of these draw calls, like the resolution of the texture we're rendering into. But this is still a 3 times improvement from the 13 milliseconds that we had before. And if, by the way, if we just turn reprojection up to 2, so we just allow a little bit of reprojection to help us out, and we take a capture for that, then we see that we're down to 1 millisecond. And so, if we can tolerate a little bit of that blurriness that comes from using reprojection, we can improve performance a lot and still leverage Unity's really great temporal anti-aliasing implementation. I know it's split. Some people use TAA, some people use submorphological anti-aliasing, SMAA. Some people are using MSAA for multi-sampling. But this is the strategy I'd recommend for using TAA, is to just try to keep reprojection frames as low as possible, lean very heavily on low sample counts and temporal denoising to get yourself to your performance numbers. Coming in here at the end of the video, actually, I realized that I forgot to mention something, which is that these numbers that we have been using in the video have all been captured from play mode in the editor. But you'll actually see a bit of a performance boost when you compile your game and build your game down to an executable. So these numbers are actually not quite accurate, and you'll actually get a little performance back when you compile your game. All right, and with that, we are at the end of the tutorial now. Thank you for sticking around for the whole time. I hope that you go and implement some of these techniques in your own Unity project, and you find that you get big speed up in terms of how long Expanse takes to render the sky for you. If not, though, and if you still have other questions, I encourage you to come and join our Discord. I'll put a link for that down in the description. And ask away. Ask any questions you have, and we can sort out how to best optimize your sky together. But until the next tutorial, for now, I'll say thanks for watching, and I hope you have a great day.